In this example, I have an arm, okay, that's rotating counterclockwise, at 5 radians per second, 2 radians per second squared, and at the instant in time I'm interested in, theta is actually equal to 90. And what it's doing is it's pushing this little particle through this path, okay, and I want to figure out, hey, what kind of normal force, what kind of force am I putting this rod, what kind of force is that putting on the particle, okay, as it moves through a smooth, frictionless path. Okay. So the first thing I'm going to do is figure out what my acceleration is, okay, again, because we want to set up our coordinates based on what I know about acceleration. Because I have polar coordinates, I'm going to set up my polar accelerations. Okay, so I have theta, theta dot, double dot shown right here. Okay, r, okay, is right here. Okay, I just plug in pi over 2 for theta into that, and I get this for r. Okay, taking a time derivative of that, this is essentially 0.2 theta to the negative 1, so I get theta to the negative 2, negative sign down here, and then times a theta dot. Plugging in pi over 2 and 5 radians per second, I get r dot equal to negative 0.4, and then r double dot is pulling out the negative 0.2 and then doing some time derivatives. So I bring the 2 down, go to negative 3. Basically, derivative of the first times the second, that's what I have here, plus the first times the derivative of the second, that's what I have here. Plugging in, again, pi over 2, 5, 2 into this equation, I get 2.4. So that's my r dot, r double dot, theta, theta dot, theta double dot. Again, we've done that several times, okay, taking time derivatives of polar equations. Now that I've got those, I can figure out my radial and transverse acceleration just by plugging in r double dot, r dot, all that stuff into these equations. So taking all those, plugging them in, I get a radial acceleration of negative 0.76 and a transverse acceleration of negative 3.8 meters per second. Again, that's the acceleration in the radial and transverse direction. Okay, so I got those accelerations. Okay, so now let's draw our free body diagram. Okay, knowing that we're going to have our coordinates in radial, transverse, polar coordinates. Okay. Now the problem here is this force is definitely going to be in the radial direction. Okay, but there's a normal force keeping this little guy on the path. Okay, so I need to figure out that angle between my normal tangential and my radial. So I'm actually going to find between my radial and my tangential. Okay, so we use that equation. Okay, where r is again 0.2 over theta. Now this is dr d theta, so again not with respect to time, with respect to theta. So again I just get the negative 0.2 theta to the negative 2. Okay, so then at this instant, again when theta equals 90 degrees or pi over 2, I can plug that in. Okay, and I can actually, once I simplify things, plug in the pi over 2, which is 90 degrees, and I get a psi equal to negative 57.5. Now what's the negative mean? Okay, so let's hear our free body diagram, right? Again, I have my force that I'm interested in, that's my radial force. I'm sorry, that's my transverse force. That's the force of the rod pushing on it. And then I have a normal force basically keeping the ball on the track, heading off in that direction. This angle is the angle between my radial and my transverse, and my tangential, which is actually in this direction, heading down and to the left. So the negative actually says, okay, well, that negative 57, I just flip it to the other side, going in the negative tangential direction, right? Because this guy is moving down and to the left. So up and to the right, that 57, I just go into between r and negative t, which is up and to the right. That angle is 57. So that's how I draw that. So essentially then I know the angle between F and NP, okay, is 57.5. Now that I have those angles, I can write my equations. Okay, so the sum of the forces in the radial direction, okay, is NP, and we're using the 32, which is just 90 minus the 57. Okay, that's this angle right here. Okay, so it's cosine. Okay, and that equals the mass times the acceleration in the r, which we just found up here. I also have my transverse, which is the force that I'm looking for, and then the NP sine of the 32.5. Okay, and that equals ma theta, which we also found up here. So solving these two equations, I can find NP from the top equation. I actually get negative answers going in the opposite direction. Okay, and F I also get a negative. So my free body diagram is drawn backwards, but the process is the same. So I could just tell them they're in that direction. So again, the key to drawing the free body diagram is figuring out the angle between my radial axis and my tangential axis using this equation here. Then using the accelerations in the radial and transverse direction, summing the forces in those directions, I can calculate what it is that I need to figure out.